Okay, so welcome to the last talk in this morning. It's our honor to have Professor Martinus Kool from Utrecht University. He will talk about Sheaves and Calabi-Yau, fourfold and virtual invariant overview. Let's welcome.
Okay, thanks to the organizers. It's a great honor to be speaking here at this wonderful, inspiring conference. So the enumerative geometry of Calabi-Yau threefolds is a very rich subject at the interface of mathematics and theoretical physics. More specifically, it involves studying Gromov-Witten and Donaldson-Thomas invariant. So in this talk, a Calabi-Yau threefold is a smooth quasi-projective threefold with trivial canonical bundle. And very roughly speaking, Gromov-Witten invariants are counts of complex curves C mapping to X, whereas Donaldson-Thomas invariants, on the other hand, count holomorphic vector bundles E over X. But more generally, we allow the vector bundles to be supported on submanifolds, complex submanifolds of X, or even more generally, we will allow them to be coherent sheaves. So I'll come back to these more precisely in a minute. But this talk is rather about a somewhat newer subject, the Donaldson-Thomas theory or the enumerative geometry on fourfolds. So by dimensional reduction, these include the threefold invariants, but there will also be several new directions. So I'll try to give an overview of this subject. Let me say in advance, it's by no means a complete overview. I'll focus mainly on a selection of examples where some new interesting connections occur. So these will depend on the dimension of the support of the sheaf or whether we're in the compact or non-compact case. First, to warm up, we'll discuss traditional Gromov-Witten and Donaldson-Thomas theory. So first, let X be fully general, a complete, just a smooth projective variety, complex numbers, and C a complex smooth curve. Then the space of infinitesimal deformations for deforming C inside of X is given by sections of the normal bundle, whereas the obstruction classes to deforming the curve to higher order all lie in the first cohomology group of the normal bundle. Moreover, for dimension reasons, then all the other sheaf cohomology groups vanish. Now let us fix some topology for the curve. So we fix the homology class and we call it beta, and we fix the genus G of the curve. Then we can look at the difference in dimension between deformations and obstructions, deformation space and obstruction space. And this is given by a well-known formula here. It's the dimension of X minus 3 times 1 minus G plus the integral over beta of C1 of X. And we'll call this the virtual dimension. So next, we'd like to vary the curve C over the space X. So more precisely, we look at Kontsevich moduli of stable maps. So these are morphisms from a nodal curve C to X. So we now allow the curve to become mildly singular, where the curve needs to have arithmetic genus G and fixed homology class beta. And we put a stability condition, namely the number of automorphisms of the map is finite. So this is a moduli stack. And by adding these singular objects, it becomes compact. That's the main point here. Now, in general, this is, let's call this space M, dropping all the indices. This will be a very singular space with several components, and therefore not really a good fundamental class. However, it's well known that it has a good virtual fundamental class. So this is a homology with rational coefficients. And it lives in degree twice the virtual dimension of the previous page. So this number over here. And this class is well behaved under deformations of the complex structure of X. And then by definition, Gromov-Witten invariants are obtained by integrating insertions over this virtual class. So these will produce rational numbers. So this is a huge subject. I will give a survey of Gromov-Witten theory here. Some of the leaders in the field are present at this conference. But let me just mention without references that this is already interesting for a point and for a curve, in which case you'll get a relation to Hurwitz numbers. For complex surfaces, you get a connection to Severi degrees, which were already studied in the 19th century. And then on the Calabi-Yau threefold X, something very special happens. This formula over here produces zero. So then you get a relation to string theory. And for Calabi-Yau fourfolds, which come back later in this talk, the virtual dimension is 1 minus g. So the only interesting cases to consider are genus 0 and genus 1, roughly speaking. So I'll come back to this later in the talk. In general, these numbers are rational numbers, but there are certain multiple cover formula in both cases which turn them into integer invariants known as Gopa-Kumar-Vafa invariants. Okay, so I want to highlight one special case that will come back in a more complicated form later in the talk. So let us consider the case where we look at the Gromov-Witten invariance of a K3 surface. So we fix a homology class beta and a genus G, so beta is an effective curve class. Then if you calculate the virtual dimension, you'll find G minus 1. So now let us fix the complex structure of the K3 surface. In other words, we look at a smooth family curly S over a smooth base B. And let's say our original K3 surface sits over 0. And I'll restrict to a contractible base. Then as you vary the point in the base, the Hodge type of beta will change. So it starts off being Hodge type 1, 1, but then when you vary in the base, it will change. And the Noether-Lefschetz locus is defined as the locus of points in the base where the Hodge type of beta remains of type 1, 1. So this will define you a divisor. But this tells us that Witten invariants have to be 0. Namely, by deformation invariance, you simply deform outside of the Noether-Lefschetz locus and you'll get 0. So all Gromov-Witten invariants of a K3 surface are 0. Now, this situation can be cured as follows. What you can do is you can make the space of obstruction smaller. So it turns out that all obstruction classes lie in the kernel of the natural map from H1 of the normal bundle to H2 of OS, which is known as a special case of the semi-regularity map of Bloch. So globally what it means is you want to remove a trivial factor from the obstruction sheaf. And the result of this is that you produce a virtual class which is only invariant under deformations inside of the Hodge locus. This also increases the virtual dimension by 1, so the new virtual dimension is G. So this process is known as reducing. It has been studied by many people. Junho Lee in differential geometry, Jun Lee, Cao-Maulik-Toda, for general type surfaces, Richard Thomas and I studied it. So this is a well-known procedure. And then you can look at the corresponding reduced Gromov-Witten invariants. And these are crucial when you look at, for instance, the Yau-Zaslov formula counting rational curves on a K3 surface, or if you want to look at the Katz-Clem-Vafa formula. Okay, next, let's say a few words about additional Donaldson-Thomas theory. So we start off here, a smooth projective Fano threefold, Yau threefold. So now we are no longer on arbitrary X. And let E be a stable holomorphic vector bundle with fixed determinant. So I won't define precisely what stability is, but we impose it so that the automorphism group of E is under control. It's as small as possible, namely just multiplication by scalars. Then again, you can look at the space of first order or infinitesimal deformations. This is the trace-free part of the first extension group, and the obstruction classes lie in the second extension group. And by stability and the fact that we're on a Fano or Calabi-Yau 3, all other extension groups vanish. So now we fix some topology. We fix the total Chern character of the sheaf, and we call it V. Then again, on the Calabi-Yau threefold, something very special happens. the space of deformations and obstructions, the difference in their dimensions is again 0, like in the Gromov-Witten case. So now we want to vary the holomorphic vector bundle X, and we allow it to become singular. So more precisely, instead of vector bundles, we will look at torsion-free sheaves. So this leads to the Giesecke-Maruyama-Simpson moduli space, parameterizing stable torsion-free sheaves over X with fixed Chern character V and some fixed determinant. So we'll call this MXV. And there's some fine print here. The stability always depends on the choice of polarization on the threefold. And moreover, in this talk, I will always assume stable equals semi-stable, which will imply that this space here is compact. So this is a compact scheme, projective scheme. Again, generally this space, let's call it M, is very singular with no good fundamental class. But it does have a virtual fundamental class constructed by Richard Thomas, which lives in homology with integer coefficients in degree 0. And then by definition, Donaldson-Thomas invariants are the degrees of these classes. And this is already very interesting when you take your rank to be 1 and the first Chern class to be 0. Then this moduli space reduces to Grothendieck's Hilbert scheme, parameterizing points and curves on X. More precisely, Z in X is a closed subscheme of dimension at most 1, and the Chern character of the structure sheaf is 1 minus V. So in this case, there's a famous conjecture due to Maulik, Nekrasov, Okunkov, Pandripande, which states that the information of DT invariants, in this case, is equivalent to the information of the Gromov-Witten invariants. And this has now been proved, it was first proved for complete intersection Calabi-Yaus in products of projective spaces by Pandripande-Pixton, and then recently there's also a general proof by Pardy. So we may hear more about this in other talks at this conference. But let me also point out that there are other interesting Donaldson-Thomas invariants one could consider. For instance, a case that I like is to take S a smooth projective surface and the total space of the canonical bundle over it. In this case, you can study two-dimensional compactly supported sheaves. And what Tanaka-Thomas and Golampur-Shashmani-Yau found is that you can use the DT theory of this setup to define Vafa-Witten invariants, which is a subject which is attracting quite some attention at the moment. All right, so let us now slowly move towards Calabi-Yau fourfolds. We'll need one foundational result, and so let MXV be one of these moduli spaces of states, denoted by M simply. We need the following structure result due to Borisov-Joyce, and it builds on an important foundational result from derived algebraic geometry due to Pantev, Toen, Vaquier, and Vezzosi. So what it is saying is the following. Suppose X is a Calabi-Yau threefold. Then everywhere, locally around each point in the moduli space, your moduli space simply looks like the critical locus of a regular function on a smooth variety. A regular function, let's call it phi. And there's also such a model in the Calabi-Yau fourfold case. So Zariski locally, your moduli space everywhere looks like the zero locus of a special section. So what kind of section? Well, you have a smooth variety A and a quadratic vector bundle on it. So E here is a holomorphic vector bundle and Q is a fiberwise non-degenerate quadratic form. And the section is isotropic, meaning that the quadratic form vanishes on the section. So any moduli space of stable sheaves on the Calabi-Yau 3 or 4-fold locally looks like either of these two cases. And sometimes it happens, this structure globally. So this happens when you're on the simplest non-compact Calabi-Yau 3 or 4-fold, namely affine 3. Affine 4 space. So here, if you look at the Hilbert scheme of points on C3 or C4, you globally have, in the first case, this superpotential, in the second case, this isotropic section. So in these cases, you have the structure of the previous page globally. And it also happens in cases where you look at moduli of representations of Calabi-Yau 3 and 4 quivers. Essentially, these are the only cases where this happens globally. Now, suppose you have this structure globally. What can you then do? So in the Calabi-Yau 3 case, you can build the following diagram. So the differential of the potential phi is a section of the cotangent bundle. So its dual will give you a map from the tangent bundle of A to, O, but it surjects onto I mod I squared, where I is the ideal sheaf of M inside of A. And then you can compose with the Kähler differential D, and you'll land in holomorphic 1 forms on A, and you can complete the diagram. So then here on the top, you get a 2-term complex of vector bundles, and the map is nothing but the Hessian of phi. So we'll call this complex the virtual cotangent bundle. And this diagram then gives a map to the cotangent complex of M, or rather its truncation. So even though here you see this presentation depends on the embedding of M inside of A, an object of the derived category, this complex here is independent of how you realize M inside of A. So it's intrinsic. And in the Calabi-Yau 4-fold case, you can do something similar. You can first start by looking at the dual of your isotropic section S. So it will map from E dual to I mod I squared, and then again you compose with the Kähler differential, you get this square here. But now you can do something extra. So you can pre-compose via the quadratic form with the differential of the section. So this is a map from the tangent bundle of A to E. And then by the isotropy condition, this composition here will be 0. So again, we'll call this 3-term complex of vector bundles on the top. We'll call it the virtual cotangent bundle, and it maps to the cotangent complex. So in the Calabi-Yau 3-fold case, what we obtain in this way, in the terminology of Berend van Tecke, is a 2-term obstruction theory, and it's symmetric. So this means if we go to the previous page, we see that this complex here is symmetric under dualization up to a shift. So let's call the dual the virtual tangent bundle. Then we have this isomorphism here. Let's call the isomorphism theta. And likewise, in the Calabi-Yau 4-fold case, this 3-term complex here is self-dual up to a shift by 2. So in this case, you get a 3-term symmetric obstruction theory. So this is all in the case where you have the superpotential or the isotropic section globally. But it turns out when you only have it locally, or more precisely if you're on a moduli space of stable sheaves on a compact Calabi-Yau 3 and 4-fold, you still always have a 2 respectively 3-term symmetric obstruction theory, omega M ver, mapping to the cotangent complex. And then this can be intrinsically described as follows. The virtual tangent bundle at a sheaf E is always the derived R hom EE, trace-free shifted by 1. And as I mentioned already before, in the Calabi-Yau 3-fold case, this will produce for you a virtual class in homology in degree 0. So in the Calabi-Yau 4-fold case, the traditional construction of virtual classes doesn't work. However, Borisov-Joyce and Thomas found a clever way to cut this complex in half, roughly speaking, and produce a virtual class nonetheless. So this virtual class lives in homology with rational coefficients, and it lives in degree twice the virtual dimension, where the virtual dimension is half of the rank of your virtual cotangent bundle. So in this case, it's no longer 0 in general. So let me make a few comments about this class. Yes, please. That's right, yes. So yeah, this class was produced in special cases by Cao and Lung. Let me also say, it works in the compact and non-compact case. And in the non-compact case, you often have some more structure. You often have a torus action T on X lifting to the moduli space, and you'll get a class in T equivariant Borel-Moore homology. We'll come back to this later in examples. But the key point I want to make is the construction of the fourfold class requires some extra data. It requires what's called a choice of orientation. So what this means is you want to have an isomorphism between the determinant of the virtual cotangent bundle and O, with the property that if you square it, you get the determinant of the pairing from the previous page. So the determinant of this map theta here. So that's an orientation. Existence of orientations was studied by Cao, Gross and Joyce, and Joyce-Uppmeyer. But it's rather non-explicit. However, if you're in non-compact cases where you have the isotropic section globally, it's often very easy to construct concrete orientations as follows. So let's assume our quadratic bundle has even rank. Then whenever you find a maximal isotropic subbundle lambda of E, this will give a trivialization of the determinant of E, and therefore it will give you an orientation. So we'll use this later on. And let me also stress that the deformation invariance is rather delicate in the Calabi-Yau fourfold case and was recently established by Yeonjun Park. So this class is invariant under deformations of the complex structure. Yeah, but it's not complete. I can tell you, yeah. Yeah, it has to do with whether -2 shifted symplectic structures behave well in families. And, yeah. So there's an assumption there which is not always satisfied. Okay, so now let us go to examples. So the first case I want to look at is points or zero-dimensional sheaves on a compact Calabi-Yau fourfold X. In this case, our moduli space will be the Hilbert scheme of n points on X. And when you calculate the virtual dimension, you'll find n. So we need an insertion. So the simplest type of insertion you can create in this way is as follows. A holomorphic line bundle L on X. Then on the Hilbert scheme, we can create the following tautological vector bundle. The tautological vector bundle Ln, whose fiber over a cluster of points Z is just the global sections of L restricted to Z. This is a rank n vector bundle, so we can take its Euler class and integrate it over the virtual class and put them into a generating series with formal parameter Q. Then a lot of years ago with Yalong Cao, we conjectured that for certain orientations, there should be orientations such that this is given by the following formula. The McMahon function on minus q to the power the integral over x of c1 of L times c3 of x. So the McMahon function is this infinite product here, and it's the generating function for numbers of piles of boxes in the corner of a three-dimensional room. This conjecture is proved in the following case. So let D be a smooth connected threefold. And let's take L to be O of D. Then Park used his virtual pullback formula to show the following identity. The Euler class kept with the virtual class on the fourfold is nothing but the virtual class of the Hilbert scheme of points on the threefold D. And the degrees of these virtual classes, so these have virtual dimension 0, have been known for quite a while. So formulae for their degrees were conjectured by MNOP and later proved. There are several proofs, one by Levine Pandaripande, one by Ju Lee, and Bernd van Tecke have a proof in the Calabi-Yau case, when D itself is also Calabi-Yau. And I should also say this conjecture was also studied by Cao and Chu, and in the setting of wall crossing, trying to generalize or dropping this assumption here by Boyko. But now let us go to the non-compact case. So let X be affine 4 space and M the Hilbert scheme of n points on C4. Then the virtual dimension is again n, and we have a non-compact moduli space. However, we have the standard torus action of C star 4 scaling the factors of C4. And I want to restrict to a slightly smaller torus where T1, T2, T3, T4 is 1. So this torus preserves the Calabi-Yau volume form. So this action on C4 lifts to the moduli space M. And even for this smaller torus, the fixed locus is in some sense very easy. It's zero-dimensional and reduced, and it precisely consists of the subschemes cut out by monomial ideals. Now, monomial ideals can be combinatorially represented by piles of boxes in the corner of a 4-dimensional room. So here I only draw the 2-dimensional analog. So more formally, these are sequences pi ABC with ABC non-negative. So you should think of this as the height in direction 4, where the total number of boxes sums up to n, and this sequence is decreasing in each of the 3 directions. So when we have such a solid partition, as they're called formally, we associate to it a polynomial. So we sum over all boxes I, j, k, l in pi, T1 to the I, T2 to the j, T3 to the k, T4 to the l, and we'll call it Z pi. And we'll also associate a Laurent polynomial V of pi to the solid partition, namely it's Z pi plus 1 minus T1, 1 minus T2, 1 minus T3 over T1, T2, T3, Z pi star. So what does this star here mean? It means replace each TA by TA inverse. So this will produce some Laurent polynomial, and more formally we view this as an element of the equivariant K theory of a point. So you see there's some asymmetry here, because 4 doesn't appear in this vector, 4 only appears in Z pi. Let us also define variables SA, so these are the equivariant first Chern classes of the TAs, and then by this Calabi-Yau condition, their sum is always 0. So then there's the following theorem, which is announced already for a while, but Yeah, that's right. In that sense, it doesn't appear. That's right. So this is a theorem with Rennemo, which hopefully will appear soon. So it's based on a conjecture in physics, Nekrasov and Nekrasov-Piazzalunga. So the theorem states the following. Suppose we equivariantly integrate 1 over the virtual class and put these into a generating series. Then we make certain explicit choices of orientations by choosing explicit maximal isotropic subbundles, such that this generating series is given by a purely combinatorial generating series, namely the sum over all solid partitions, q to the power the size of the partition times the sign, which I'll comment on in a second, and then times the Euler class of minus v pi, where v pi was defined on the previous page. And over, this is given by the explicit formula you see here. It's the exponential of minus S1 plus S2, S1 plus S3, S2 plus S3 over S1, S2, S3, S4 times Q. And as Artwan pointed out, you should view this exponent here modulo the relation that the sum of the SI's is 0. So then it looks more symmetric. So what is this sign here? This sign is very interesting. So mu of pi is the size of pi plus the number of boxes AAAB in pi with A smaller than B. Again, this formula was first discovered in physics by Nekrasov-Piazzalunga, but using completely different techniques. They use supersymmetric Yang-Mills theory on C4. Say there's another proof of this formula by Cao, Zhao, and Zhou using different methods, namely degeneration, but their work does not give a formula for the signs. There's also a k-theoretic version, which is the version we actually prove. And well, there are many ingredients to the proof, but let me just highlight three of them. One is a sort of Atiyah-Bott localization formula in the fourfold setting due to O. Thomas. And two other important ingredients are Okunkov's rigidity principle and his notion of factorizable sequences. So roughly speaking, this localization is used for the first equality, and these two are used for the second equality. Okay, next we move on to curves on a compact Calabi-Yau fourfold. So as before, M bar Gx beta is the moduli space of stable maps, but now we also introduce M marked points. So for each marked point I, we have an evaluation map from the moduli space to X. So again, we fix beta in the genus G, and then the virtual dimension is 1 minus G plus M. So we'll need some insertions. So we fix delta, a class in H4 with integer coefficients. Then in genus 0, what we do is the following. We put one marked point, we pull back delta along evaluation and integrate over the virtual class. This gives a Gromov-Witten invariant GW0 beta delta. In the case of genus 1, we put no marked points, then the virtual dimension is 0, and we simply take the degree of the virtual class. So these are rational numbers which were studied by Clem and Panderipande, and they propose certain multiple cover formulae which turn these into integers conjecturally, called N0 beta delta and N1 beta. Now, what Cao-Maulik and Toda did is they give a conjectural sheaf theoretic characterization of these integers you see on this page. So this should be viewed as a sort of Donaldson-Thomas Gromov-Witten invariance in the fourfold setting. So what do? They fix a chunk beta n in cohomology, and we look at the Hilbert scheme parameterizing points and curves on X. So here we always take the chunk character of the structure sheaf to be V. And then when you calculate the virtual dimension, it's again n. What's interesting here is the virtual dimension does not depend on which curve class beta you have. However, we do need insertions. So what we do is we fix the universal subscheme Z in the product of X times M. So M is this Hilbert scheme. And what we do is we take our class delta from the previous page and we pull it back from X to the product. And there we cap it with the third chunk character of the structure sheaf of the universal subscheme and push it forward. So this produces a primary insertion tau 0 delta. So what you can do now is you look at, you fix n and you define I n beta delta to be just tau 0 of delta to the power n, and you integrate it over this virtual class. So this, by construction, is integer. And then what Cao-Maulik-Toda propose is the following conjecture. They say let's sum over all points and curve classes, these I n beta deltas over n factorial, and then q to the n, capital Q to the beta. And they say it has the following structure. It's the product over all curve classes of some universal function to the power n0 beta delta times another universal function to the power n1 beta, where these are the numbers studied by Clem and Panderipande. So this is the conjecture, and there's a whole list of examples in which this conjecture has been verified. All right, next we move on to surfaces on a compact Calabi-Yau fourfold X. So now we fix a chunk character 0, 0, gamma beta n. So gamma is a surface class, beta a curve class, and n point class, if you like. And I also put this shift here for convenience. We fix such a class, algebraic, and we look at the Hilbert scheme parameterizing points, curves, but now also surfaces on X. So more formally, closed subschemes Z in X of dimension at most 2, where the Chern character of O of Z is V. So by this shift here, this implies that the holomorphic Euler characteristic of OZ is N. And now what you find is that the vertical dimension does actually depend on the surface class. So it's N minus half gamma squared, intersection of gamma. Okay, so let us go to what is perhaps the simplest case you could consider, namely the sextic Calabi-Yau fourfold in P5. And let's go to a special sextic, namely one that contains a plane. So the general sextic does not contain a plane, but special ones do, like the Fermat sextic. And let V be the Chern character of O of S. Then unfortunately, when you calculate this virtual dimension, it's a negative and it's not even an integer. So there are multiple reasons why the virtual class is 0. And a heuristic explanation for what's happening here is as follows. The family of all smooth sextics, curly X over B, with our original sextic over 0. Then let's go to a contractible neighborhood of 0. And then again we have a Hodge locus, like in the case of curves on a K3 surface. So we can look at the locus of points in the base where gamma remains of Hodge type 2,2. So generally when you deform, the Hodge type of gamma, which originally is 2,2, may change. And what you'll find is Hodge locus in the base is a complex analytic subvariety of codimension 19. So this means you can always deform out of the Hodge locus, and by deformation invariance you get 0. So the upshot is that, like in the case of curves on a K3 surface, you want to reduce the theory. So here is a somewhat technical slide on deformation theory. And this slide actually has nothing to do with Calabi-Yau 4. So this works on any smooth projective fourfold and any surface, or more formally, closed subscheme of dimension 2 on X. In fact, it even works for any closed subscheme on any smooth projective variety if you shift the dimensions a bit. So let's denote the ideal sheaf of Z by I. Then we have the following diagram. We have H1 of Tx. These are the first order deformations of your fourfold. And then we have a Hodge theoretic obstruction map. So this is contracting with gamma. So this lands in H3 of omega x. So this map here measures the obstructions to deforming gamma as a 2,2 class, as you deform X, your fourfold. And on the other hand, we have a scheme theoretic obstruction map, which lands in X2. So this measures whether you can deform Z along while you deform X. So this is contraction of the Atiyah with of your shifted vector field with the Atiyah class of IZ. So it's called the obstruction map. And these two talk to each other via Bloch's semi-regularity map, which was generalized later by Buchweitz and Flanner. So this map is the trace of cupping with the Atiyah class. And then this diagram commutes. So here there's nothing special about Calabi-Yau, but then this diagram becomes special in the case of Calabi-Yau fourfolds. So in that case, this X2 is self-dual by Serre duality, and H3 of omega x is dual to H1 of the tangent bundle. And the first thing that happens is that under these dualities, the semi-regularity map becomes the obstruction map. That's the first special thing. And on this side, also something special happens, studied by Carlson, Green, Griffiths, and Harris. So the Hodge theoretic obstruction map is given by a bilinear form B gamma. So it takes two shifted vector fields V and W, and what it is, it contracts gamma with V and W, and then you cut with the holomorphic volume form and integrate. So now let us call rho gamma the rank of this map B gamma, and let us fix V a maximal subspace in the deformations where B gamma is non-degenerate. Then what we do is, in the case of curves on a K3, we made the obstruction space smaller, we do the same here. So instead of x2, we look at the surjection induced by this map here onto V dual, and we take the kernel of it. So roughly speaking, what this means is this V here is a normal direction to the Hodge locus, and we want to trap our virtual class to be only deformation invariant along the Hodge locus. So this is achieved in a work with Yonghan Bae and Yeonjun Park, using work of Kim Lee and Kim Park. What we show is there exists a natural reduced virtual class in homology with rational coefficients, which is deformation invariant only along the Hodge locus. And the degree in which it appears is twice the reduced virtual dimension, which is n minus half gamma squared as before, but now plus half of rho gamma, this codification of the Hodge locus. And what's interesting here is these here appear in F theory as well. They're related to the Gukov-Fafa-Witten potential and the G4 flux. Yes, please. Right.
There is still a subhypothesis curve.
Yes. Sometimes, yeah. It turns out sometimes this reduction may be enough, but this is just the first reduction. It could be that in specific examples, you may have to reduce further for curve classes. Yeah, that's a good point. So potentially this has some, some relation to the variational Hodge conjecture as follows. So suppose we have a family of Calabi-Yau fourfolds, curly X, our original Calabi-Yau sitting over 0. And let us assume we have a family of chunk characters, gamma t, beta t, n. And let's also assume we are already in the Hodge locus. So all the gamma t's are 2, 2 and beta t's are 3, 3. Now let us also say we have a family of Hilbert schemes, curly m. So this parameterizes subschemes on the fibers of your family. And let the original Hilbert scheme be M0. Then if you happen to find a non-zero invariant on the central fiber, it will remain non-zero everywhere over the base. In other words, gamma t must be represented by an algebraic class everywhere on the base. Now, why is this the correct class? So that's given by the following theorem with Bae-Park. So inside of there's a locus called the semi-regular locus. By definition, this is the locus where the semi-regularity map of Bloch is an injection. So the way to ensure that Hodge theoretic deformations and scheme theoretic deformations collide. So Bloch already proved that if you're semi-regular, you're a smooth point of the Hilbert scheme. And what we show is that for surfaces on Calabi-Yau fourfolds, it's an if and only if in the following sense. A point is semi-regular if and only if the Hilbert scheme is smooth of dimension equal to the reduced virtual dimension at that point. So what this is saying is that at the semi-regular locus, the reduced class is the fundamental class. So trivial. So let me mention some examples. If you start with the sextic and any complete intersection surface in there, and V is the chunk character of your surface, let the type be D1, D2, D3, then it turns out your surface is always semi-regular. And in this way you can produce Fano surfaces, K3 surfaces, general type surfaces. And also the virtual dimension is 0. So in this general type case here it's 3. Actually in this talk I used a loose definition of Calabi-Yau. You're allowed to take your fourfold to be hyperkähler or abelian. And something nice happens in the case of Lagrangian surfaces, but let me skip this. So in the final part of the talk, I'd like to look at surfaces on non-compact fourfolds. Or rather, we look at Nekrasov's origami gauge theory. So first, I put a slide on the traditional ADHM quiver, which is related to instanton as you are instantons on S4. But for me, in the quiver setting, it's the following quiver. We fix V to be Cn and W to be Cr, a framing moduli space. And we look at the following quiver. We have vertices W and V and arrows I, J, X1, X2. And we look at representations of this quiver. So linear X1, X2, I, J, satisfying the ADHM equation. So commutator X1, X2 plus IJ is 0. And we put a stability condition, which says that if you act repeatedly by the loops on the image of W under I, you generate all of V. So there's a free action of GLV on here by coordinate change on V. And we call the quotient MRN, or simply M. So you can read about this in Nakajima's book or lecture notes. You'll find this is a smooth variety of dimension 2Rn, and it's symplectic. It is non-compact. However, there is a big torus acting. We have a C star squared acting on the loops and a C star R acting on W by the diagonal action. And under this huge torus, the fixed locus is zero-dimensional and reduced. So then we can form what's known as the Nekrasov partition function, or a version of the Nekrasov partition function. We can equivariantly integrate 1 over MRN and put them into a generating series. So this is a building block for many other invariants that are of interest in gauge theory or enumerative geometry. There's also a sheaf theoretic interpretation of this moduli space due to Barth. It's pairs pi, where E is a rank R torsion-free sheaf on the projective plane, with a framing, the line L infinity at infinity. We require the sheaf to be trivial of rank R. And we fix the second Chern character. Now, Nekrasov discovered a very interesting quiver, which is a big generalization of this ADHM quiver. So let me introduce his quiver. So let 6 bar be the collection of sets A, B, where A and B range between 1 and 4. 4 bar is the set 1, 2, 3, 4. We have an involution on 6 bar, so for each set we can take the complement. We take V to be Cn, as before, but now we fix 6 framing vector spaces WA, which are C to the RA. And then he tells us to look at the following quiver. So we have 6 framing vertices, WA, and an internal vertex V. And we look at arrows IA, JA, going in and out, and loops X1 up to X4. And we look at representations. So we look at linear maps satisfying for all capital A, consisting of small a smaller than b, equation. So commutator XA, XB plus IA, JA is 0. And then he says there are some more relations we should consider, namely if we go in with IA and we go out with JA bar, we get 0. And relations XA bar, IA, JA, XA bar is 0 for all A bar and A bar. And the stability condition is as before. The joint images of the WAs after acting with the loops generates all of V, and then GLV acts freely on here. So this is what we consider. In general, this moduli space is very singular, unlike the traditional ADHM moduli space, but it has a very nice feature. It is globally the zero locus of an isotropic section, as I mentioned before. So it has that global isotropic zero locus description. So therefore, by the previous discussion, it's again symplectic, but in this virtual shifted sense. Now, this moduli space is non-compact, but there's also a big torus acting. So T1 up to T4, where the product of the T's is 1. So this is the same as in the Hilbert scheme case. We require this Calabi-Yau condition. So this torus acts on the loops. We have 4 loops. And then we have a whole bunch of framing actions. So for all A in 6 bar, we have a C star RA acting on WA diagonally. So here we use coordinates WA alpha. Yes? Well, yeah, this will be in 2 slides. attempt at giving a sheaf theoretic description. Not quite. It's well, yeah, it's related to that, but yeah, I'll give you the precision. Okay, so this acts on MRN, and well, the fixed locus is here dimensional reduced, and it's just a huge collection of Young diagrams. Lambda A alpha, where A runs in 6 bar and alpha runs from 1 up to the rank RA, where the total size of the number of boxes, the total number of boxes is n. Then we define for each A consisting of A smaller than B, we define a polynomial Z lambda A. It's the sum over all alpha, sum over all boxes ij and lambda A alpha, Ta to the I, and then we also put this framing parameter WA alpha here. And the advantage of having this global isotropic zero locus model is that you can construct explicit maximal isotropic subbundles which will give you orientations. So therefore by O. Thomas we get a virtual class in equivariant homology. And the virtual dimension is given by an interesting formula. It's minus the sum over A in 3 bar, where 3 bar consists of 1, 2, and then RA bar. And you should not be annoyed by the fact that it's virtual dimension. So we're working here with equivariant Borel-Moore homology, so there are interesting classes in negative degree. Okay, so what we now do is we form the origami partition function. We equivariantly integrate 1 over these classes and put them into a generating series, and we normalize by the leading term, which is often called the perturbative term, where the instanton number is 0. Okay, so now there's some more notation we need, borrowed from Nekrasov. So for each fixed point lambda bar and each capital A is A smaller than B, we already defined Z lambda A on the previous page, this polynomial here. And now let's define some more quantities. N of A is the sum of all the framing parameters, WA alpha. Phi of A will be the minimal element of the set A. And then there's this crucial quantity, T lambda A. It's NA Z lambda A star plus TA TB, NA star Z lambda A, minus a quadratic term. So PA here is 1 minus TA, 1 minus TB. And for the next page, I'll also use P1, 2, 3, 4. It's 1 minus T1 up to 1 minus T4. So this character here is, or this virtual representation is a familiar object. So up to a factor, it's just a tangent representation of the original ADHM moduli space at the partition lambda A. So NA, it's the sum of all the framing parameters here. Yeah, of this framing vector. So then there's the following theorem in a work in progress with Arbesfeld and Lim. And in physics, of course, it originates from Nekrasov's work. So this origami partition function is combinatorially described by the sum over all lambda q to the size of lambda, and then the Euler class of some character minus v lambda. So v lambda is explicit in terms of the data of the previous page. It's the sum over all A in 6 bar of P of phi A, T lambda A plus P A bar NA times the sum over B not equal to A, Z lambda B star, and then some quadratic term. So this weight you can find in Nekrasov's PPS CFT papers, which originate from around 2015. Now, the most interesting part in this theorem is what's not there. So you find that there's no sign, unlike the case of the Hilbert scheme. So what we show is that all the orientations, if you use this halving of your virtual tangent bundle, are plus. So I think this is a new fact in the literature. And this allows you to recover, so there are several examples. You can make specializations of this ADHM quiver, this origami quiver. If you take R12 equal to R and all other RAs equal to 0, you just get the old ADHM moduli space, and you get the old Nekrasov partition function, but with an adjoint matter here. So you should think of this as a sort of local Vafa-Witten partition function, singular 4 manifolds. You can also reduce to a case where all the framings involving 4 are 0, and then there's also a critical locus description of your moduli space, which was studied by Seubelmann and collaborators using cohomological Hall algebra. But now let me get to your question, is there a sheaf description? So let us work a little more generally. Let X be a smooth projective 4-fold with an effective divisor such that twice the divisor is anti-canonical. Let us fix a Chern character in cohomology with first 2 entries 0. And let us fix a pure one-dimensional sheaf on this divisor. And it's important that this divisor is allowed to be singular, and even non-reduced. Then we look at the following moduli space, Mx framed of V, consisting of pairs E, phi, where E is a pure 2-dimensional sheaf on X, and phi is an isomorphism between the restriction of E to D and F. So we want 2-dimensional sheaves that transversely hit this divisor at infinity and then produce F. And we fix the Chern character. Okay, let me take back what I just said. To be singular, but we do take it reduced. Then what we show with Arbesfeld-Lim is that this is a quasi-projective scheme with a universal family and a 3-term symmetric obstruction theory. And pointwise, over point E, phi, the virtual tangent bundle is R hom E shifted by minus D, twisted by minus D, shifted by 1. And since twice D is anti-canonical, this complex is self-dual. And then if you combine with the PhD thesis of Theodore Spade, you'll find that whenever you have an orientation moduli space, you'll get a virtual class by the work of O and Thomas. So let me mention one example. So suppose X is the product of P1 4 times, so P1 times P1 times P1 times P1, and let us fix a 3-fold at infinity. So I'll use coordinates x0, x1, y0, y1, z0, z1, w0, w1 on these factors. So then I have this singular 3-fold at infinity, and this is what I take as my divisor. And I take a specific pure one-dimensional sheaf on this divisor, which I won't write down here. Then the claim is, if you go to this moduli space and you define invariants by T localization, this also produces the origami partition function. But there's one to stress. We are not able at the moment to construct orientations directly on the sheaf side. So we borrow the orientations from the quiver side. We also don't show that this is globally isomorphic to the quiver moduli space. What we show is there's a match at the level of fixed points, and at each fixed point, the K-theory classes of the virtual tangent bundles match. Yes. Yeah. So this is a geometric way of building origami. Although, again, it would be very nice to actually relate this moduli space globally to the moduli space of representations of the ADH quiver. So maybe a final slide. You can also look at 3-folds inside of a 4-fold. So in physics, these are called tetrahedron invariants, only Yan and Zheng, and they were studied in mathematics by Cao-Monavari. So you take the union of the 4 coordinate 3 planes in C4, and again you take a sheaf on this singular 3-fold, but now you take a 3-dimensional sheaf. So what you take is, you take the direct sum of the push forward of the 8th copy of C3 to the power Ra, and you push it forward to C4. So this produces for you a 3-dimensional sheaf on C4. And then you look at Grothendieck's quad scheme of 0-dimensional quotients of this sheaf, where the length is n. Cao-Monavari show is that this has an O-Thomas virtual class. There's a big torus action here as well, and what they do is they put these equivariant degrees of the virtual class into a generating series, and they prove that it's the McMahon function of a sine times q to some equivariant power, minus s1 s2 plus s3, s1 plus s3, over s1, s2, s3, s4, as we saw in the Hilbert scheme case, times the sum over a of RA SA. I think this is a good point to stop.
Okay, any question?
So, just Nekrasov's magnificent form, there was this thing that you have the C-fold, you have the 6 coordinate Harvard planes, right? And imagine that you have the sheaf, two-dimensional sheaf supported on this thing. And how can I get that one dimension?
Yeah, so that you can by removing this threefold at infinity. Then you get C4, and you get. So that's the part you remove when you remove the framing at infinity. Yes, yes. And then what remains is a torsion-free sheaf, and when it's torus fixed, it's just given by a bunch of partitions.
Geometric concept. Just the order.
Yes, and that's
Boxes just be concentrated.
yes, and that's the case here too.
Obstruction. But you can have non-Calabi-Yau, but X of self-extensions of sheaf, even if there is a non-trivial canonical problem, it's just similar. If the sheaf doesn't see the canonical.
Yeah, you mean if you somehow are in a setting where all your sheets are outside of the divisor representing the canonical bundle.
And the sheaf was order, right? So it was non-Calabi-Yau, but X was two. I mean, X1 and X2 were isomorphic.
Right. So there could definitely be cases where your sheaf doesn't see the canonical divisor, and then you could also apply that. Yeah.
The origami is class space C4, but they, for example, we are not adding into compact cycle. It's not alone for threefolds.
So firstly, from the geometric description, you don't have to take, so now for this talk I took the divisor to be reduced, but I think it's possible to take this divisor non-reduced and allow sheaves supported on thickenings, so then you'll get nestings of partitions. So that's certainly one thing you could do. But you want to do Calabi-Yau 3 times C?
Yeah, I was just thinking, instead of the ADHF quiver, you can put any quiver for a Calabi-Yau threefold. Instead of the ADHF quiver, you can replace it by any quiver for Calabi-Yau threefolds that are any node, and you just take the formula to be that threefold times C, so you're not adding any node to the quiver, and you just change the framing.
Yes. So they expect that after localizing, you'll get the threefold invariants.
Okay, so this would not be new invariants.
Well, depends, because even in some sense, even in the case of, well, if your sheaves will be supported in the threefold, then no, but if they would thicken, then yes. So even the C4 case is the canonical bundle over C3, but it does give you new things because the zero-dimensional schemes thicken in the fourfold direction. So it will give you new things in general. Yeah.
You think it's possible?
On the sheaf side, there are already plenty of constructions along those lines. Yeah, so if you would vary this f somehow, that you then start counting curves so here, this is a concrete fixed sheaf that we fix. So that it's like you have this Arbesfeld-Lim paper where they look at moduli of pairs, as they call it. So it's always a sheaf mapping to a fixed, to some chosen sheaf. I should maybe say chosen. Yeah, and that's what's happening here as well. So we pick a chosen sheaf on D, which I've suppressed here, but after the talk I can write it down. And for that chosen sheaf, we look at such pairs. And in fact, we realize this as an open subset inside of a Arbesfeld-Lim type moduli space. So that's how the first part of this theorem is proved. Yeah, that is very interesting. Yeah, that we certainly didn't study. Right. Yeah, so that would be interesting.
Thanks for the last question. Any other one? Okay, if there's another question, thank the speaker again.
Yeah, I can show you the sheaf if you like.